Oh man. All right, record the physics video. Okay. Let's close that. Hi. So, we're back. Today we're going to talk about time-dependent perturbation theory again, and we're going to work up to applications involving transitions in atoms. So we'll be thinking about, say, having a hydrogen atom in some state, and then we'll try to understand if you actually have electromagnetic radiation and that perturbs the hydrogen atom system, what are the probabilities of making transitions, say from the ground state to some excited state? And so today, the first thing we're going to do is just a quick review of the formula that we had last time for transition probabilities. And this is a very general formula that would work in any kind of quantum system. And then for this video, the goal is to just understand what does that look like in the case where our time-dependent perturbation is a sinusoidal perturbation. Okay, and that will be very useful for applying to electromagnetic radiation because at least in the case where you have radiation of a particular frequency, then we can understand that as a sinusoidal time-dependent electric and magnetic field. Okay, so let's review. So our setup is that we have a Hamiltonian where initially you have some time-independent Hamiltonian. So this might be the hydrogen atom Hamiltonian. And then we have a time-dependent term in our Hamiltonian that we're assuming is relatively small. And so we're also going to assume that that turns on at some time t equals 0. So before t equals 0, the Hamiltonian is just the time-independent part. And now at t equals 0, this time-dependent part turns on. And let's say we have some initial state at that time, which is an energy eigenstate of H0. So maybe it's the ground state, or maybe it's some other excited state. And so our goal is to figure out what is the probability that after some time, after this time-dependent perturbation is acting, what is the probability that we'll find state B, some other energy eigenstate at the time t? Okay, and so our formula in the end, it looked like this, assuming that B is not equal to A. And so there are two things that come into this formula that we'll have to understand. One of them is this omega BA. And so that is just the difference in energies between the state that we're interested in making a transition to and the initial state. So we take the difference in energies and divide it by h bar, and that gives us some frequency. Okay, so that's a factor. This e to the I omega t is a factor in the integral that we're going to have to do. What's the other piece that's important? It's this matrix element, H prime BA. And so the definition of that is to take the state, your final state that you're asking about, and take the matrix element of the perturbation between that and the initial state. And so this is going to be some particular function of time. And so if we want to calculate this transition probability, what we want to do is calculate that matrix element. That will give us some ordinary function of time. And then we're going to integrate that against this exponential function from 0, or actually generally from the initial time when the perturbation turns on to the time t when we want to ask about the probability. So that's the general formula. Okay, so now we want to specialize a little bit and understand what happens when the time dependence is not some general function of time, but what happens when we have h prime of t equals some operator V, which we assume is time independent, times a cosine function with some particular frequency, omega. And I could have picked a sine function here. It doesn't really matter. Actually, the results are going to be the same. So this is our Hamiltonian that we're perturbing by. So we have a sinusoidal perturbation. And the reason is that that's actually a realistic kind of time dependence for a lot of our applications. Okay, so now we basically just plug this in to our expression above, and it turns out then we're going to actually be able to do the integral over time and approximate that and get a relatively simple final expression. Okay. So what does this look like? So we plug it in and we get PB of t equals 1 over h bar squared, integral from 0 to t. We still have our complex exponential depending on the difference of energies. And now we have cos of omega t prime times the matrix element of the operator V between state B and state A. So we have all of that squared. And now this is simple because this matrix element doesn't depend on time anymore. And so in terms of our integral, we actually have a very explicit integral that we can do. And it's actually a really easy integral. So if you have the exponential of I omega t times the cos of some other frequency times t prime, we can convert that into an integral of exponentials by using this kind of standard formula where we write cos as e to the I omega t plus e to the minus I omega t prime over 2. It's just using the standard formula for cosine in terms of exponentials. And then our entire integral is just a sum of, the integrand is just a sum of these two exponentials. So that's a very easy integral to do. And I'm going to write down the answer here. So it ends up that we can pull out this matrix element squared divided by h bar squared. And then we get something that, it looks a bit complicated, but we'll simplify it very soon. So we get one term here where it's a fraction. The denominator is going to be important for us. In this case, it's the sum of these two frequencies. And let's erase that here. And then the other term looks similar. It's a function of the difference of our two frequencies. Okay, and just to remind you, the omega BA, it's not really a frequency associated with a perturbation. It's just the energy difference between the two states divided by h bar. So that has units of frequency. And then the omega is the actual frequency of our time-dependent perturbation. Okay, and so now you can analyze this function, and what we're interested in is understanding how does the probability kind of change if we vary the frequency of the external perturbation. Okay, so we can imagine having our quantum system and sending in an electromagnetic wave of one frequency or of a slower frequency or a faster frequency. And so it turns out that there's this interesting phenomena that's a lot like resonance in classical mechanics. It turns out that you get a much bigger effect, a much bigger transition probability if the frequency that you are driving the system with matches the difference in energies for your states. Okay, so this is, so just mathematically, what happens is that, so if omega is either equal to EB minus EA over H bar, or if it's equal to EA minus EB over H bar, then one of these two energy denominators is going to 0. And now you might think that the function would blow up then, but actually the numerator also goes to 0. But nevertheless, the end result is that this entire function that we have here is peaked. It has a maximum when the omega is equal to the omega BA. Okay, so let's write that down. So this thing in the absolute value is most significant near omega equals the absolute value of omega BA, which is equal to the absolute value of EB minus EA over H bar. Okay. And so just to make the notation a little bit simpler, I am going to call that omega 0. So we have our quantum system, we have this initial state, we have this final state. That final state might have a higher energy or it might have a lower energy. Regardless, we take the difference of the two energies, and then the absolute value of that over H bar is what I'm calling omega 0. It's sort of a natural frequency associated with our system, and what we're saying is that if the driving frequency is similar to that, then we're going to get a larger transition probability. Okay, and so basically what we can do is then approximate. So we can, let's say omega is close to omega BA, then this second term here is going to be much larger than the first term, and we can approximate the entire expression by the second term. And then we can write that second term, we can simplify it down to some real function, so we have this absolute value squared. Then we're going to use the result that e to the ix minus e to the minus ix over 2 is sine of x. Okay, so we can use that to simplify this expression, and the result of that is, so then PB of t is approximately equal to VBA squared over h bar squared. And then what we end up getting is, once we apply that identity, we end up getting sine squared omega minus omega 0 t over 2 over omega minus omega 0 squared. So you may want to stop the video for a few moments and just make sure that you can see how to go from this expression to this expression once we ignore one of the terms in the absolute value. Okay. So let's visualize that. Let me actually make a plot of this probability as a function. So we're going to fix the time for now, and we'll just make a plot of this thing as a function of frequency, just so you can see what that looks like. And so let's do that down here. So on our x-axis here, this is going to be the driving frequency of our system. And on the y-axis here, it'll be the probability. And we're going to plot this at a fixed time, so fixed t. Okay. So what does it look like, this function sine squared? It's like sine squared x divided by x squared, and it looks like this. Where this guy is omega 0. So you see that the probability is sharply peaked at omega equals omega 0, and then it falls off if the driving frequency is not very similar to this natural frequency that we get from the difference of energies, then we're not going to have a very big effect. Okay, so let's just write that down. So our conclusion is that for fixed t, that the transition probability is highly peaked when the driving frequency matches EB minus EA over H bar. Okay, and just to emphasize again, this could be a situation where the final state that we're talking about has a higher energy, or the final state that we're talking about has a lower energy. And so we can visualize that. Okay, so now let's say we have a quantum system with various states. Okay, and so let's say this is our initial state A, and maybe we have a particular driving frequency, and so maybe for this state here, the difference in energies divided by H bar matches that. Okay, and so that means if we apply that perturbation, then there's going to be a higher probability that we'll get a transition up to that state. Okay, because that difference in energies divided by H bar matches this frequency of the perturbation that we're adding. But there might also be another state down here, let's call this B prime. So that one also has the same, or approximately the same difference in energy between A and B prime as we had between A and B. And so basically our time-dependent perturbation, which has this particular frequency, it can stimulate transitions up to some higher energy state. Okay, and so then the physics of that is that the system absorbs energy from the outside, from our whatever this system is that's interacting with it, or we can have transitions down to a lower energy state, and in that case our system gives up energy to the external system. Okay, and so again, so far we haven't really focused on any particular quantum system, so this applies to an arbitrary quantum system with an arbitrary time-dependent perturbation that's sinusoidal. And in the next video we're going to start focusing on atomic or molecular systems where our external perturbation is actually coming from electromagnetic radiation. And then we'll start talking about what is the particular form of the Hamiltonian for that kind of situation.